In this video, we're going to discuss the solubility of gases. So gases can dissolve in a liquid reasonably easily. There's gas above, and every once in a while one of those molecules impacts the surface and bounces off. And this happens a lot, but every once in a while one gets inside. The liquid can solvate it, interact with it. Water can induce dipoles as it interacts. For various reasons, some gas molecules get dissolved. Well, over time, those gas molecules can drift and get back to the surface and escape. And so, given a while, the particles will leave. In fact, you see this anytime you open a soda can. There's a lot of gas dissolved initially. When you open it, it starts to escape, and slowly over time, more and more bubbles escape, and your soda goes flat. Originally, there's quite a bit more gas dissolved than should be. It's a supersaturated solution versus when the can's open and exposed to the atmosphere. So how does that work? How did we get more in to begin with? Well, again, there's an exchange. There's a leave rate as the particles randomly move to the surface and can escape, but there's also an enter rate. How often do the gas particles get into solution? Well, this is dependent on how much gas there is. If you have a lot more gas, then there's just a lot more impacts, and the enter rate will be a lot greater. You'll have more chances one of them gets into the solution. Your solubility of your gas is actually dependent on the pressure of the gas outside the liquid. So in a sealed Coke bottle, there's a lot of pressure. If you ever try to squeeze them, they resist it. There's a lot of overpressure. Usually a pop bottle is about 2 atmospheres of pressure, which means you can effectively get twice the number of impacts on the surface as you would in a normal atmospheric pressure. So when you first open that bottle and a bunch of that gas escapes, suddenly there's not nearly as much gas above, and our enter rate decreases. Well, there was plenty of gas dissolved, and so over time they start to escape, and therefore the rate starts to decrease as there's less and less gas in the solution to escape anymore. This is why bubbles will happen quickly early on and then slow down. There's less CO2 in your drink, and therefore less of it able to escape. Well, how do we calculate it then? Basically, there's a solubility of your gas. That's going to be equal to the partial pressure of your gas, whatever the actual pressure of that gas is above the surface of your liquid, times a constant. Well, this is Henry's law. And so that's the Henry constant, Kh. A few Kh values for helium, N2, O2, CO2, ammonia, just to give us a feel here. Our Kh, in this case, we're going to use atmospheres for our partial pressure. So our Kh units are going to be in moles per liter atmosphere. This means that when we multiply it by the pressure, we'll just have moles per liter, which would be the solubility. And so it's a constant just to adjust for our units. For helium, however, that value is 0.00037. For dinitrogen, it's 0.00061, almost double. For O2, it's 0.0013, so an order of magnitude bigger. For carbon dioxide, it is 0.034, 2 orders of magnitude. And for ammonia, it's around 59. So what's going on? Why are these so very different? Well, for smaller gases that just dissolve, as these first 3 do, you need a molecule that's better able to interact with water. Helium is small, single atom, noble gas. This is not very polarizable. It really holds its electrons tight. It's not really going to interact and have a dipole induced very strongly by the water. Dinitrogen has a triple bond. Most of its electron density is tied up in that. And so while it can interact and be polarized a little, O2 actually can do that more. It's only got a double bond, it's got more electrons that aren't tied up, and so it's a little bit more polarizable, despite being a little bit more electronegative. Yet when you get to CO2 and ammonia, this starts to jump, because what's really happening here is that these are reacting. Carbon dioxide can interact with water to make carbonic acid. This is part of the acidification of the oceans as we raise the CO2 levels in the atmosphere. Ammonia can make ammonium hydroxide as it dissolves, so that's very readily available. And so ammonia just starts reacting with the water to create ammonium hydroxide. As a result, you can get a great deal of ammonia to dissolve. It's not really just a nonpolar gas bumping around inside waiting to escape. It's reacted with the water molecules. So Henry Law's got to recognize whether or not a reaction is occurring or whether you are just straight up dissolving the gas. This is part of why we see such wildly different constants. However, let's go ahead and give a calculation here. Let's find the O2 solubility in 25 degrees Celsius water. Well, these are the Henry Law constants for water at 25 degrees Celsius. And actually, these constants will change for every gas-solvent pairing and at every temperature. Remember that your gas solubility is temperature dependent, and so we have to have a different constant for every single pairing and every single temp. But here are the ones for water in 25 degrees Celsius. Well, at sea level, we have 1 atmosphere of pressure, but only about 20% of it is O2. So the partial pressure of O2 is really about 0.2 atmospheres. So what's our solubility of the gas? Well, that's going to be 0.2 atmospheres for the oxygen's partial pressure times the 0.0013 mole per liter atmosphere for the Henry Law constant. As a result, when you calculate this out, you'll get 2.6 times 10 to the minus 4 mole per liter. This is not a particularly large amount of O2, and in fact, that's kind of an issue for a lot of life in the ocean. They have significantly less oxygen available compared to humans. 2.6 times 10 to the minus 4 moles per liter. Let's compare that for somebody breathing oxygen from the atmosphere instead of from the sea. If you were to say, hey, pressure volume equals nRT, and we've got a pressure of 0.2 atmospheres, we're going to look at that 1 liter. Let's figure out how many moles would be in the gas. So instead of dissolved in a liter of water in the ocean, how many moles are in the gas phase for that same liter? So we'll divide the R over and the T. Well, we're in atmospheres, so 0.0821 atmospheres, liters over mole Kelvin, 298 Kelvin, which means our moles in a breath of 1 liter is 0.008175, or 8.2 times 10 to the minus 3. So we actually have a lot more oxygen when we're breathing from the atmosphere than animals do that are in the water. For the same volume passed through, we have almost 40 times more oxygen available, because very little of it actually succeeds at dissolving into the ocean. And so we can find the solubility for a gas in liquid if we know the Henry Law constant and the partial pressure of the gas. And then a quick example here to show it and compared to just how much oxygen is in the atmosphere. Since the gas is bombarding the surface and not every bombardment succeeds at entering into the liquid, in general, you're going to have far more gas above than in solution, unless your gas is reacting with the solution. That can complicate matters much more.